Next talk is by Vishal Saxena, and I think Vishal is online. Yes, I can see him. So, Chitra, would you be doing the introduction?
Sure, I'll do introduction for Professor Vishal Saxena. Thank you, sir, for your kind presentation. Again, we are welcoming to you to give a session on neural network circuits. And a short introduction of Professor Vishal Saxena goes like this. He received the BTech degree in electrical engineering from IIT Madras in 2002 and MS and PhD degrees from Bose State University in 2007 and 10 respectively. He is currently an associate professor with the Electrical and Computer Engineering University of Delaware, where he directs the analog mixed signal and photonic integrated circuits lab. His research interests include CMOS photonic interconnect, RF and millimeter wave photonic ICs, data converters, and neuromorphic computing and low power circuits for edge AI. He was a recipient of the 2015 NSF Career, 2016 AF OSR Young Investigator Program, and 2019 DARPA Young Faculty Awards. He currently serves on the steering committee of the IEEE MW SCAS conference and ISCAS VLSI committee. He was an associate editor for the IEEE Transactions on Circuits and System 2 from 2013 to 2015 and from 2017 to 2019. So over to you, Professor Vishal Saxena, for your presentation. Thank you.
Thank you for the kind introduction. Can you see my shared screen, Bhaskar?
I can see a blob, a blue square. I don't see a presentation.
Okay, I have two screens, so it's doing something strange. 1 second. Okay, let's try again. Okay, how about now? Let me put in the presentation mode.
I can see the presentation, but not yet in the presentation mode.
Okay, now?
I can see the presentation, but this is in a classical PowerPoint mode.
Yeah, can you see
Yes,
me
can see the
slides?
presentation
Oh,
now.
okay. Yeah, two screens make Zoom confused.
I was thinking that you are from the president's home state, so maybe that's causing some issues. They're checking whether you can talk.
No. It's just Zoom has its own issues. Anyways, thank you for the kind introduction and for inviting me to provide this talk. So, as you know, neuromorphic computing, especially analog neuromorphic computing, is a vast area. So we'll just focus on some select topics which pertain to challenges and recent advances in NVM-based neuromorphic computing ICs. So this is the outline. We'll briefly go over the devices we are trying to use for neuromorphic computing and what are their challenges. In order to understand the circuit, we need to understand the underlying algorithms which we are trying to realize in neuromorphic ICs. And then we'll go over some of the circuits, recent IC architectures, demonstrations, and the trends, followed by conclusion. So neuromorphic IC and edge AI sort of go together because they're trying to solve the same problem, which is how to realize low power embedded inference, classification, and probably some on-chip learning at the edge at a very low power and a small form factor. So there's a growing need for this low power embedded AI to reduce reliance upon cloud and wireless infrastructure and to enhance data privacy and also allow personalized AI models where your own device can learn a model which is specific to you instead of having a shared model on the cloud. The overarching goal is to achieve the energy efficiency of the brain, which is foreseen by eliminating von Neumann bottlenecks by computing inside memory, which is also known as the in-memory computing paradigm, and by employing analog mixed signal techniques to reduce power consumption as much as possible. So going over the basics 101 of neuromorphic computing is we compute in a spike domain, and which is inspired from how the brains and the neurons compute. So this is essentially based upon the understanding which is emerging from computational neuroscience. And here, what we have is that we have neurons which perform computations based upon asynchronous spike. So what they do is the neurons are connected with each other through synapses at the where the axons meet the dendrites. And you can imagine a neuron to be, let's say, generate spikes which are weighted by the weights or synapses and integrated on the neuron. So we integrate and sum all these incoming spikes which are weighted by the synapses, and then they are integrated into a membrane potential. When the membrane potential crosses the threshold, this neuron spikes as well. Now, the interesting thing here is the neuron spikes in the forward as well as in the backward direction. And then if I zoom into one synapse, the correlation of these two spikes can be used to realize localized learning, which is known as synaptic plasticity. So there are various plasticity mechanisms. A simple one is STDP, and then there are emerging three-factor learning rules and their variants. And these can be mapped to backpropagation algorithms as well. And as I said, axons are used for routing. There are a lot of issues which are still being uncovered in computational neuroscience, such as neuromodulator feedback, the roles of astrocytes and glia. So this was the basic of neuromorphic computing. Now, we derive inspiration from the brain because it's highly energy efficient, the most energy efficient computer we have in the universe. And it is because of its massive parallelism. So human brain has 10 to the power 11, that is 100 billion neurons and 100 trillion synapses connected in a massively parallel fashion. The computing is event driven, which means that the neurons communicate and compute using sparse spikes, which are sort of digital-like signals. They're not really analog. They're sort of digital-like signals. And the energy is consumed only which and a spike event occurs. So the energy consumption is very low because of event-driven computing. And one important feature of the brains is that learning is localized, highly localized, where the neural networks learn through synaptic plasticity, where the weight of the synapses is modulated to change based upon the localized events. So if you look at the neuromorphic computing space, started around 1980s or 1990s, and the goal was bioemulation. They were trying to build CMOS circuits using subthreshold CMOS to emulate neurophysiological behavior and implement the ion channel type equation and see, what kind of or simulate neurophysiological circuit in order to understand the activity or learning in brain, activity of brain, not learning per se. Then, with the resurgence of neural networks and deep learning AI, around 2014, I would say, digital ASIC started showing up. First was True North by IBM, which is event-driven asynchronous digital IC for inference. And then recently, Intel's Low-E-High also support on-chip learning. These are digital asynchronous digital ICs, which employ neuromorphic computing. Then also there's a space of CMOS mixed signal ICs, where the synapses and neurons have been implemented using subthreshold CMOS, and now recently the synapses are being implemented, or we are attempting to realize them using emerging memory arrays to reduce their neurosynaptic density, to increase the neurosynaptic density and reduce energy consumption. So this is the neuromorphic computing space we have. And the goal here is the goal is to actually realize, as I said, deep learning at the edge at very low power. So this is a comparison from a survey of the AI accelerators that we have. So we see at high end, we have data center based accelerators, which consume very high power, but they give you very high throughput, right? So if we look at throughput per watt, which is a metric of energy efficiency, we get these lines. And with neuromorphic, what we are trying to do is push this very low power, which is in terms of teraops per watt, which is basically you're getting high throughput with very low power consumption. So we are looking at sub-watt or in the order of 100 or tens of milliwatt power, but providing up to 10 teraops per watt or higher operations per second of throughput. So this is where the analog neuromorphic ICs they're supposed to push the limit of low power computing. So if you look at the emerging memory devices, they're attractive because they're low power. They use lower voltages for set reset, and with advances in devices, these voltages are continuously going down. So the energy per bit in programming and reading them is low compared to traditional devices such as flash memory. These allow very high density integration. We can actually stack them in 3D on top of CMOS. And so they pave the path for very high density. And more importantly, if we want to realize learning on chip, these are highly amenable to in situ synaptic plasticity. What I mean by that is we can implement the localized learning rule by exploiting the behavior of these devices itself, right? So this is a big draw or a factor because of which these emerging devices are of interest. Now, if we compare these devices, compare actually all the memory devices. So we have the classical SRAM and DRAM, and then NOR flash. And among the newer devices, we have PC RAM, which has been around for some time, but has regained renewed interest. And then we have STT RAM, which is a magnetic type memory, and resistive RAM, and very recently ferroelectric FETs. So what we see here is with the emerging memory devices, the cell size is small. The latencies are getting lower and lower, and the energy per bit is fairly small. We can get up to 0.1 picojoule per bit of write energy, which is significantly lower compared to flash devices. The endurance is an important factor. For example, for NOR flash, the endurance is about 100,000 cycle. But for these RRAMs and STT RAM and FEFET, it's of the order of 10 to the power 8 or higher. Now, in terms of multi-level cell capability, which tells you how many bits of weight I can store on a single device, they have demonstrated 3 to 5 bit per cell. And we'll discuss more about that. And the NOR flash actually can go up to from 4 to 8 bit. So NOR flash, if you're just looking at density from density point of view, is still very appealing. But from energy point of view and endurance, this new emerging devices also have a compelling case. There are advantages as well as now disadvantages. So there are a lot of challenges with these devices, and I will discuss them in the next few slides. So in this talk, we'll mostly focus on resistive RAM because it's available in Foundry platform, and we can start building circuit with this. Okay, so most of the results I'll show you will be about RRAMs. Now, RRAM can be broadly categorized at two types: CB-RAM, which is conductive bridge RAM, and OX-RAM, or oxygen vacancy or oxide vacancy based RAM. Now, in CB-RAM, in these devices, the basic idea is this: you have two electrodes. One is active electrode, other is inactive, and there's an amorphous medium in between, which could be a chalcogenide glass or transition oxide. And so what happens is that by application of voltages, filaments are formed in the amorphous medium. And by changing the length or width of this filament, we can modulate the resistance state of these devices. Okay. So if we look at the switching in CB-RAM, so if we apply, positive and negative pulses, let's say a triangular sweep, what we see is if we start with a pristine device, as we start increasing the voltage, the silver in this electrode starts getting oxidized and it is attracted towards the other electrode. As we keep on increasing the voltage, a filament keeps on building and eventually it connects both the electrodes and the device enter a low resistance state. Now, if we reverse the process, apply negative voltage, the filament is dissolved and we come back to the high resistance state. So we can cycle between low resistance and high resistance state by changing the width and length of this bridge that is formed in the amorphous medium. There are a lot of details such as electroforming. So for example, first time you build these devices, it's like cracking a popcorn. You have to use forming, where you apply a higher voltage so that the device's a filament track can be built across the amorphous medium. Now, interesting aspect to look at is their threshold voltages. So this is a program threshold here at point C, which when you cross, there's a abrupt change and the device switches to a low resistance state. Similarly, there's a raised threshold voltage where the device returns to high resistance state. Now, one important factor is you will see when you look at device papers is the compliance current. So most of the time, or actually all the time when the devices are characterized, they limit the current that can flow through the device. And by using small compliance current, we can actually restrict the thickness of and the length of this bridge, and we can achieve intermediate states, which give you analog-like states in the RRAM. Aux-RAM has similar behavior. When we apply the positive voltage, a bridge of oxygen vacancies is created, and that is conductive. And when we apply negative voltage, the bridge is dissolved. So this way we can go back and forth between high and low resistance state. The difference with Aux-RAM is it requires little higher voltage for program and erase compared to CB-RAM, and it is more symmetric for program and erase operation. Endurance for Aux-RAM is in the range of 10 to the power 8 or 10 to the power 9. Now, these memories can be arranged. The corresponding memory can be arranged in various configurations. The simplest one is 1R array, where you have a 2D array, and every intersection of bit line and word line, you have a single RRAM device. And that's a passive crossbar array because you don't have any transistor in there. Then the next one is 1T 1R cell, which is more popular, where you have a single transistor which acts as a selector, and it is also used to set the compliance current for the device. So 1T 1R cell, as we will see later on, they are more suitable for analog type operation. And there are various other configurations where they use a diode as a selector or back-to-back flipped cell. But 1R and 1T NR is what we will focus on. Now, if we look at the broader area of using memory arrays for edge AI, so essentially deep learning and edge AI boils down to vector matrix multiplication, where you are computing the activation of the neuron based upon the multiplication of the input vector with the weight matrix plus some biases, and then you apply a sigmoidal function, activation function. But essentially the computation boils down to this W times X, which is vector matrix multiplication. So the way vector matrix multiplication is realized in VMMs is that you have on the word lines, each word line is driven by a DAC. Every intersection has one device, could be 1R or 1T 1R. And then on the columns, you have ADCs. Now, the inputs are VIs. So you can do a simple Kirchhoff current law where voltage over resistance of this device produces currents which are summed in the bit lines, and their sum is then digitized by the ADC on the columns, and you get a digital code out. Now, this type of VMM is interesting and has been explored with various type of memory devices, from DRAM to flash and now RRAMs and FEFETs, because it provides you very high density in memory computing. It is lower precision than GPU, but the energy per inference could be 3 orders of magnitude higher, the energy efficiency per inference. So this is the building block of a lot of edge AI systems, analog mixed signal edge AI systems that are being investigated. So, but what you see here is there are limitations, there are challenges. You need DAC and ADC. So a DAC on every word line and an ADC on every bit line, and their design complexity, area, energy, they just add up. And think of having several arrays on a chip, you will have tons of ADCs and DACs. So that is one limitation. The other limitation is we are essentially performing analog multiplication. So if VIs are analog quantities here and WIJs are analog quantity, we really want this device to perform 4-quadrant multiplication that we all know is very hard in analog. And this is hard because these devices, the weights, may be nonlinear with voltage, right? So when you have voltage dependent nonlinearity, the result of this multiplication will show that nonlinearity. One could say we could compensate for those nonlinearities. The problem is these nonlinearities are process and temperature dependent. So with different process variations and temperature, the nonlinearity will vary, and it will impact the overall accuracy of the network. Other issues, as we will see later on, these weights can change with time. So this is an example of a paper from CICC 2017, where inference, VMMs for inference were realized in flash memory array. So as I said, flash is still a very valid candidate. A lot of work can still be done with flash. And so they use embedded flash in CMOS. I believe it was 55 nanometer CMOS. And each cell can be programmed up to 4 to 8 bits. And it has 10-year retention. The issue which happens in these kind of, if we use this VMM, as you can see, they are performing analog multiplication, and we need these linear regions. Only in these linear regions, we can perform 4-quadrant multiplication. But there's a lot of PVT dependent, process and temperature dependent variability, which actually degrades the overall performance of these architectures, and it's just very hard to calibrate. Okay, so the bottom line here is, if I use analog inputs, analog weights, and perform VMM, the device's nonlinearities and their dependence on PVT, it doesn't support, it doesn't provide good performance. We need to think differently. So that brings us to spike encoding. So what is essentially happening in spike encoding is, the input, instead of applying an analog vector, we are converting that analog input Vi into a pulse train or a spike train, okay, where it's encoded using a bi-level sequence. So input, instead of analog vector, one input instead of analog value is actually a pulse train. So you can think of a vector of pulse trains here at the input. And this can be done in a lot of different ways, to do this pulse coding. And now my weights are only processing binary levels. And when you draw a line through 2 points, it's always linear. So we don't have the problems of nonlinearity of these devices. And then the outputs. So what is happening is, the DACs and the ADCs are getting transformed into spike encoders and neurons. Okay, so essentially we can eliminate this ADC and DACs by using spike domain processing or spiking neural networks. And probably this is the reason why nature uses spikes, because it has to work with highly variable, low resolution, nonlinear neurons and synapses, which are available in our biology. Okay, so this is why spike encoding is lucrative, because not only it can lead to lower energy because of event-driven operation, but we can use these nonlinear, low-resolution devices to perform analog computation. Now, if we try to visualize the simplest 1R array, how do we compute with 1R array? So we could have, let's say, if you have a 3-level neural network, we could have 3 arrays, 3 crossbar arrays, which are connected, one after another in a succession, and each array is 1R. So we'll have input neurons and output neurons, and there will be some other peripheral logic to be able to write to these array and perform or map some learning rule to these neurons. And if we take a slice here, it looks like a presynaptic neuron or pre-neuron and a postsynaptic neuron, and the synapses are sandwiched in between. The neurons generate spike, they compute using spike, and the weight can be updated by using the correlation of these spikes, which is governed by spike time independent plasticity or STDP learning rule. So this is a demonstrator of STDP, where you have 2 input neurons and 1 output neuron with 1R devices sandwiched in between. So what it says is that if my output is correlated with the input, which means it immediately comes after the input, that weight is increased, delta W is positive. And if the input is not correlated with the output, which means it's not contributing to the output spike, that weight is decreased. So this is a Hebbian type learning, and we will show later on that this can be used for some sort of learning, unsupervised learning in these neural networks. So this is STDP rule. Now, to show how STDP can be realized in 1R synapses, 1R arrays, is we have to do something called waveform engineering. So we have to carefully craft these waveforms, the spike waveforms, so that their temporal correlation, delta T, can be translated to program and erase pulses. So here, if post spikes comes after pre-spike, which means the weight should increase. So here, if we take their difference, the resulting pulse crosses the program threshold of the device, and the conductors is increased, the device is programmed, and in the other case, the device is erased. So these are known as long-term potentiation and long-term depression. And this is the well-known STDP type learning curve. But we'll see later on, we are not just limited to STDP type learning. Now, coming back to devices, the number one issue is the variability. The device thresholds, as I described, they are variable from device to device and from cycle to cycle. So if you cycle the same device, you will see different switching voltage in every cycle. So that is because of the amorphous nature and the nature of the way these devices switch by movement of ions. Now, the switching characteristics depend upon the initial forming step. And that highly depends upon the compliance current, as I mentioned earlier. So we can see is by controlling the compliance current, I can get different distribution. So if I use a large compliance current, this is example for CB-RAM we characterize in our lab. For large compliance current, I get more digital-like resistance state, which is the distribution is narrow. But if I use a smaller compliance current, I can get a wider spread or more analog-like states. And you can visualize that as analog states are supported by weak filaments. And if you have a thick filament, which is bridging the two electrodes, then it's more digital-like device. So what we learn from here is that compliance current is very important for realizing multi-level cell capability. And the variability in device is inherent to the, to the nature of physics of this device. And we have to work with that. As I said, the stochasticity is similar to variability, is same thing. Where the switching is voltage dependent because of variable threshold voltages. And it also depends upon the program pulse duration as well as voltage. So there are a lot of parameters to fine tune when working with these devices. The next challenge is endurance. So synaptic endurance basically means how many cycles I can write to it, how many times I can write this device. And that determines whether I can use it for on-chip learning, continuous learning, or only for few times learning. So for example, a flash memory has only 100K cycles of write endurance. So it is best suited for inference because you don't want to write to it all the time. So on-chip training, which is intensive, write intensive, is probably not best suited for flash devices, better suited for inference. Now RRAM and phase change memory, since they have much higher endurance, 10 to power 8, 10 to power right cycles, so potentially they are better suited for on-chip learning because you can keep writing to them without wearing them out. But overall, the algorithmic consideration derive which device to use and which device has a better use case compared to other. It also depends upon the application we're looking at. The next challenge is the low resistance state. So this is often ignored in literature. So if you look at the distribution, this is a distribution of resistance. On the lower end, which is the low resistance state, the resistance is in the range of 10 kilo ohms or 5 kilo ohms. So imagine a neuron driving thousands of these synapses in parallel in 1 hour configuration. We are looking at driving less than 10 ohms load, right? So if we have less than 10 ohms load, we are talking about hundreds of milliamps of current for one neuron, which is just not practical. So this actually would be the number one showstopper when you start building transistor level circuits. You really need to figure out a way to have to have a larger resistance to drive. If you take 1R array, they are very challenging to drive. So we need some techniques to increase the resistance. And 1T 1R synapses help there, as we will see later on. The next challenge is relaxation. So what happens is, let's say we are able to successfully program multiple states. So in this case, they are showing 9 states. It's a recent paper from last year, IEDM. So in RAM, 1R RAM, they are able to realize 9 states. But within 60 seconds, the state relax and their distribution changes. So you can think of as if the states are smudging into each other within 60 seconds of programming. So that's something we need to take into account. There are some other studies which were reported where you can show that if I write 16 states, within 30 minutes, the variance of these distributions starts to increase and the weights kind of start smudging into each other. So this has to be informed to the algorithm, overall algorithm, that the weights will smudge, will kind of diffuse into each other immediately after write. So relaxation happens immediately after writing, and in the long term, there's a resistance drift. So this resistance drift is device dependent. The nature may be different in phase change RAM, but in our RAM, you can think of it as if, with time and temperature, the variance increases. So if I program into certain, let's say 8 states, with time and with increasing temperature, the variance of these states will start increasing. Again, they will start smudging into each other. So it increases with the root T of time and temperature values. So this is something we need to manage. So you may have to refresh. So the impact it will have on your model, the neural network model, is that the accuracy will drop. Initially, there will be a gradual drop, and suddenly there will be a drastic drop in accuracy. And for smaller data sets, not a problem, but as we increase the complexity, it may be an issue. So this is something which needs to be looked into, whether you need to refresh the arrays periodically or work with lower resolution devices or build this into training, or some strategy which handles the drift and relaxation. Now, so as I said, the 1T 1R architecture is more amenable because it lets you to set compliance current so that you can set the device into an analogous state or multi-level state. So there are various ways, couple different ways you can use a 1T 1R cell. And what you have is a word line which drives the gate, and then a select line, SL and bit line. And to program, you apply a high voltage on the select line while the bit line is connected to 0. And for erase, you flip the configuration. You apply a reset voltage on the bit line while the select line is pinned to 0. So all these things need to be handled by the on-chip circuitry, the peripheral circuitry, all these voltage switching. The reads are performed with lower voltage, could be in the range of 100 millivolt. And as I said, forwarding requires much higher voltage just the first time the device is being initialized. So all these things have to be incorporated in the circuit, peripheral circuits. Now, there are two ways we can drive this device. Either I can drive from here, which is a select line drive. Then it looks like a memristor in series, or a programmable resistor in series with a switch. Or I can do a word line drive. Then it looks like a common source with source degeneration. Both have their pro and cons. And this really depends upon when you try to build your overall architecture. But you could treat this cell like a resistor, programmable resistor, or you can treat it like a common source with source degeneration transconductance. So both are possible. We are working with both of these topologies. Now, integration. So very recently, so to be able to build reliable circuits and to be able to work with 1T 1R arrays, we really need integration of these devices with CMOS. We have worked with bare arrays made in lab, but they just don't scale. You need reliability and the ability to work with in situ circuits. So this is one example you can go through the references where the devices are integrated in the back end of the line of a CMOS process. And then we can build 1T 1R cells and also build a peripheral circuit on the same die. So such platforms are very important for IC exploration. So for more realistic neuromorphic computing, we typically work with 2T2R arrays where 2 transistors and 2R ramps build one weight, which is a signed weight. So you can have positive and negative weights. And each array is realized using a crossbar of 1T1R with peripheral circuits. And the weight is GM plus minus GM minus. So it's a signed weight. Now, if we want to do STDP or some modification of STDP, that is also possible. We presented this work in ISCUS and TCAS, where we have to do waveform engineering, just like we did with 1R arrays. We have to do waveform engineering where the neurons generate certain type of pulses when they spike, and the overlap of pre-spike and post-spike can result in program or erase pulses dropped across the device. So you can go through a lot of details here, but the idea is that this can be mapped to a large range of rules, not just STDP, but it can be mapped to backpropagation derived rules as well, where we can use error feedback to modulate the weight change. Okay, so this is really generic, can be used in a lot of with a lot of algorithms. So summarizing the devices, in-memory computing is interesting from low power realization. And we have 2 flavors, VMM for edge AI and neuromorphic computing that works with spikes. NOR flash allows straightforward implementation, but mostly suitable for inference because of its lower endurance. Emerging devices allow higher density and can provide on-chip training, but they have their own challenges, such as the drift of the state, lower retention time, and variability. And Foundry platform integration of RRAMs or any such device with Foundry platform is essential for circuit exploration, and that still is very sparse, but it's happening. So you can build these circuits using these foundries. Now, I'll just provide a brief overview. Learning algorithm is a vast area in itself, and I can spend 3 hours just teaching that. But let's go over this overview. So there are 3 broad type of learning algorithms which are available. The first is transfer learning. You train the network elsewhere on a GPU or something and then transfer to the on-chip neural network. The second is unsupervised learning, which is more STDP-like. And third is adapting backpropagation. So modifying backpropagation, enhancing it so that it can work with spiking neural networks and on-chip RRAM arrays. And there are a lot of hybrid schemes as well. So transfer learning is essentially what we do is we make a model we make a standard ANN model and train it on GPU. And we take the topology and the weights and biases and map to an equivalent spiking neural network on a neuromorphic device. That could be a digital neuromorphic device or something custom built. There are a lot of steps which I will not go into details, but what we need to do is we need to make a continuous neuron model. So what they have done here is there's a model which maps firing rate to the input voltage, and then they have fitted a differentiable model. So like the red one, and this differentiable model is used for training the network on GPU. And then the resulting weights are mapped to the spiking neural network, and there's some post-processing called weight normalization so that the neurons do not oversaturate or under spike. So you have to put them in a sweet spot where you get the best classification accuracy. So there are a lot of steps. And this is a cartoon, or not a cartoon, or a simulation capture of how to visualize these transfer learning neural network. So this is a 3-layer neural network on 28 by 28 MNIST, and you can see how the input spike trains are arriving, and each convolutional layer and pooling layer is processing, and then you have the inference at the output. Now, that was transfer learning. The second is semi-supervised, unsupervised learning of these of SNNs. So what we do here is, and we published a few papers on this, is we stack these convolution layers, and each layer learns using STDP and winner-take-all networks. And so we have 2 such convolutional layer which learn in unsupervised manner, and at the output we have a standard softmax layer, which assign the labels, because eventually you need to assign the label. So what happens is that the layers, the inner layers, convent layers, they learn in an unsupervised manner, and they learn to pick, simple patterns at this level, at the first layer. Second layer learns to pick different features. And by combining these features, we can, build this classification engine. Now on MNIST, the accuracy we reported was 98.4%. So it's not, so the accuracy is not very close to what you will get with standard backprop, but this type of learning has its own advantages. For example, it's very robust to catastrophic forgetting. It can learn sample by sample with some modification. And the only issue is that you cannot keep on stacking. As we keep on stacking these unsupervised learning layers, it doesn't give any benefit. So maximum 2, beyond that, the accuracy tapers off. So you really need some sort of backprop to provide feedback from the top classification layer so that the inner layers can use that. So unsupervised learning has its own limitation, but what we see is robust to catastrophic forgetting. It can learn individual tasks on a sample by sample manner. Now, there's a lot of work recently being done on adapting backpropagation algorithm to SNNs. And so what they do is they have to solve this credit assignment problem across layers. And mapping backprop to hardware or these kind of memory arrays is not straightforward. There are a lot of things which are not bioplausible and also not amenable to hardware design. So a lot of steps have been, a lot of challenges have been solved. For example, symmetric weight requirement, where the transpose of the weight matrix should be available in the backward path, that has been solved by using random backprop. There are a lot of other things that have been solved. I'll refer you to this paper to read. But a lot of progress has been made where the backprop reduces to 3-factor learning rule, which can be mapped to the on-chip hardware. So there's a lot of potential here. It's just that the circuit and devices, their design is a little bit lagging. So there's a lot of work to be done here. So I'm showing you comparison. You can find the details here in this review paper from this year. So what we see here is I'm comparing spiking neural network algorithms for MNIST dataset. And what we see here is that the transfer learning gets very close to actual deep learning. The performance loss is very marginal. So transfer learning is actually ready for prime time. But on-chip learning, they are getting there. They are in the 98.7% accuracy range. They're getting there. Actually, it's not too bad. But transfer learning is actually the easiest to build on chip. Now I'm showing the comparison for CIFAR and ImageNet, more complex data sets. So what we see is the transfer learning. So here the state of the art with ResNet was 95% on CIFAR, and transfer learning reaches 88%. So it's getting close to the actual deep learning. And for ImageNet also we have similar trends. So from here, what we can surmise is that it's easier to build transfer learning on chip, and the work is in progress for on-chip learning. Actually, on-chip learning we will see is very hard with these devices. So summary of algorithm: spike-based neural networks are ideal match for hardware because they can work with these devices and deal with their non-idealities. And transfer learning is ready for deployment with marginal performance loss, and adapting backprop to SNN has yielded success. So this is a good path to investigate, where we can take these spike-based backprop algorithms with surrogate learning and random backprop and map them to the AI hardware. Now, finally, we come to mixed signal circuits for RRAM arrays. So if we want to build peripheral circuits, or we want to do any sort of computing, let's say transfer learning to begin with an array, we need to be able to program the array, right? So for example, actually every chip should have a transfer learning mode, so you don't have to learn from beginning. Now, if you need transfer learning mode, I need to be able to initialize the weights. So for each synapse of, I should be able to write a predetermined weight, and which means that each cell needs to be selected and programmed to one of the multiple states. And that is done using a program and verify algorithm, which I will show next. And then we need DACs on the word line and ADCs for readout. And then there's a controller sitting somewhere on the chip or off chip, which synchronizes this whole operation. And then we also need on-chip interconnect, on-off chip bus or interconnect, so that you can apply the inputs, have the controller mux in, and then have multiple arrays talk to each other. So the multi-level cell programming is performed, as I said, using a program and verify scheme, which is technically is called ISPP algorithm, or incremental pulse program strategy. It's similar. It's actually derived from flash world, for the multi-level cell flash memory. So what they do is that they use a state machine where the target is to reach a desired resistance state for the device for a selected 1T1R cell. And so we could do it one way, whether you could erase it all the way. Here you can erase it all the way and then bring it down by applying set pulses of increasing amplitude. So what we do here is we apply a small set pulse and then read the device. So program and verify. And if it hasn't reached the desired state, we increase the pulse voltage. And we keep on doing it till we reach the target state. So now there are many possibilities. So what we see here is this is a typical distribution for our RAM device, 1T1R cell, where the distributions are like this. So higher resistance state has more variance, more sigma. So we could space the states such that they are based upon sigma, or we could linearly space them as well. Basing on sigma makes more sense because then it will be more tolerant to the variability. And this the nonlinear mapping has to be accommodated in the top level algorithm. So these ISPP algorithm are needed to initialize or to transfer the weight to the array. So these circuits need to be built with the array for each array. Now, we'll come back to the circuit level architecture, but let's say if we were to do on-chip learning. So if we have to do on-chip learning with 1R synapse, we need neurons, mixed signal neurons, that can generate these spikes while following the waveform engineering I showed earlier. And so these are event-driven neurons. Okay, these are asynchronous neurons designed using switch capacitor circuit. And the idea is that normally they are in integrate mode. So they are configured in integration mode, where there's an op-amp and that is configured with as a leaky integrate and fire circuit. So all the spikes they arrive at this virtual ground, they get summed up, integrated, and the membrane potential drops with each spike event. And then there's a leakage also. Now, there's a comparator, a synchronous comparator sitting here that compares the membrane potential with the threshold of the neuron that could be fixed or could be digitally programmable as well. The moment membrane potential crosses threshold, the circuit is reconfigured and reconfigures itself to a firing mode. Okay, so it's event driven. Normally it's in low power integrated mode. When there's a firing event, it configures itself to fire mode where it acts like a buffer. And it pushes or drives spikes in all the direction. There's some more detail of this buffer I'll describe next. And this circuit can also support various algorithms. So I have a discharge mode here, which supports competitive learning. So here, if some other neuron fired first, it will go and discharge other neurons so that they cannot fire. So this is for STTP-based learning. But any type of algorithm can be mapped into the switch capacitor structure of this event-driven neuron. So in the integration mode, the op-amp is in low power mode. It just keeps on integrating. And there's a comparator sitting and waiting to comparing with the threshold. And when it is configured as a buffer, the op-amp is powered up. Its bias is increased so that it can drive a lot of synapses in parallel. Now, when we work with these devices, which are also being researched. The material system is not determined, they are not well characterized. So it's a good idea to have some programmability in the chip. So our neuron was highly programmable. We could configure the heights, the time constants, pulse widths, and everything so that it can work with a wide range of device parameters. Now, what we had is the op-amp we saw in the neuron. It was a class AB2 stage with dynamic biasing. So when it enters the fire mode, the current in the class AB stage is increased so that it can drive a large number of synapses. So nominally it is in few microamps, but when it fires, the bias current is upped. So it can drive a large amount of resistive synapses. So this we showed several years back. So here it was interfaced with a CB-RAM, a few CB-RAM devices. And this is the measured spike pulse, and correlation of two spikes can erase or program a cell. So eventually this demonstrated a Pavlov dog circuit with associative learning on chip. And here we can see that, when the sound of bell and the food, they are presented together, the neural network learns to associate them. And next time, whenever there's a sound of bell, the neural network will fire. This is the hello world of neuromorphic computing. Now, as I said, 1-hour arrays are not suitable because of, you have to drive large amount of resistance, so a lot of energy wasted. And you also need the select transistor for other purposes, such as setting the compliance current. So this is a 1T variation, which showed recently. This is a 1T 1-hour variation of the neuron. So it works similarly. It can work in multiple modes. Normally it's in leaky integrator mode, where it integrates the current from this compound synapse, which is a common source with source degeneration. And then when it crosses the threshold, it fires. And then when it fires, it pushes back this waveform so that the device can undergo, whatever the learning rule dictates. So this circuit, is customized for the type of learning rule that is determined by the top level algorithm. So this is the part of the co-design: device, circuit, and algorithm co-design. And all of them have to work together to realize, the functionality. This is the simulation result for this 1T1R neuron. So you can see that, it keeps on integrating, and then it on spike event fires, and it generates the right pulse waveforms so that, the STDP or 3-factor learning rule can be affected in the device. This is a performance comparison of these neurons. So you can see most of the neurons don't support on-chip learning. So what is happening is, you will find an integrate and fire neuron, but it won't be able to drive any resistance. Since RRAMs are resistive loads, if it's designed for capacitive drive, right, then there's a problem. So these neuron circuits have to be rethought of, so that they can actually drive the synapses, and not, building them using ideal building circuit blocks. So you really have to have the drive capability for these neurons. Now, coming to the last section, that is IC level demonstration. So these are the recent trends. So early neuromorphic, and you can see all these trends are from last 2 years. And that is because very recently it's possible to fabricate RRAM in a CMOS, integrated with the CMOS in a foundry process. So early neuromorphic ICs, they were binarized RRAM weights. We can look at this reference from 2020. And so they have peripheral circuits to write to the array. They are 2T 2R arrays, and they use as binary weights. And then they are sense amps, which read out, and lot of neural networks can be mapped. I think it was 1 kilo size memory array. Then other trends are that most IC, actually all of the ICs, are for inference only application, right? So they use transfer learning, and full chip implementation is limited to 2-bit per device resolution. So this is because of the challenges with multi-level cell and retention of RRAM, that they are limiting to 2-bit per device resolution. And on-chip learning is still an open problem. They are not successful. They haven't been successful demonstrations so far in a large on-chip array. Then in terms of large arrays, they only started in 2020 ISSCC. You can look at this paper. So this is a neuromorphic IC. It is done in fabricated in 130 nanometer CMOS with OXRAM type RAMs. You can see the array here. It's a 65K 1T 1R RAM with about 256 neurons. And you can see these rows of word line drivers, word line, bit line drivers, select line drivers, and then you have registers for getting data onto the chip and perform the ISPP and readouts. So this circuit, this chip was made for RBM type, RBM, LSTM, RNN type networks, and they demonstrated RBM network with actually 225 neurons in one layer and 60 in other. The essential point here is that it reached 74 teraops per watt, which is much beyond the limits we were looking at. The line was 10 teraops per watt. So these are really low power and they can realize a large variety of neural network algorithms. So this was 1T1R array. And if you look at the neuron circuit, it's just a simple common source amplifier with CDS, correlated double sampling. So all the mixed signal techniques we learned in the context of ADC design or filter design, they all show up here. So you really need to know your analog really well. This is another inference IC, again in 130 nanometer CMOS with our ramps. And this is 2T2R array. So each 2T2R cell realizes a signed weight like this. So you apply voltages so that this current is integrated on an integrate and fire neuron. And this integrate fire and neuron also forms a part of a LPAR ADC. It's a sort of SAR ADC for your VMM applications. So you can apply, the inputs are pulse coded. The cells are 2T2R. Integration is performed in analog domain. And the integrated output is converted to digital using this form of SAR ADC. So they showed 784 input, 100 intermediate hidden nodes, 10 output nodes with FPGA backend, and about 94% MNIST accuracy and 78 teraops per watt energy efficiency. This is another demonstrator with 1R array. You can see there's a lot of involved interesting analog IC design, switch capacitor type ADCs to read it out. And you can follow this reference here. This is a comparison of NVM-based neuromorphic ICs for deep learning. So what we see here is on-chip learning, mostly they are transfer learning. On-chip learning is very less. If there was any on-chip learning, it was very simple network with very simple patterns and not shown for MNIST. The only successful candidate was this work from IBM, and they used phase change memory. So I didn't focus on phase change memory, but you are welcome to look up for this reference. Other factor is that the energy efficiency is actually getting to that range. It's actually reaching 100 teraops per watt, which is orders of magnitude higher than what purely digital ASICs can do. At least 2 orders of magnitude higher energy efficiency. So the trends, summarizing the trends, so we are still in the early phase of neuromorphic ICs with our RAMs. Early ICs have showed binarized weights or MLC multi-level macros, or they use unit-weighted cells. Most large-scale ICs have limited themselves to inference-only application using transfer learning. 1T1R arrays allow better control of weight programming because it allows ISPP. The multi-level cells are limited to 2-bit per device precision. So there are a lot of challenges if you want higher density bits per device. Relaxation and resistance diff degrade model performance. So IBM's work with PC RAM actually compensated for this in the software. But for RAM, there hasn't been much work which has looked at performance with the drift at the array level. So a lot of these are open problems. Communication between arrays needs attention. A lot of work needs to be done because as the chip size grows, it'll be very difficult to get all those thousands of input into the chip and between arrays. So we need some sort of network on chip, probably open source, so that everybody can use it and build their own chips. So in conclusion, mixed signal neuromorphic ICs, they're promising for higher energy efficiency. It gives us something to do in research. But the challenge is that the the exploration is spurred by integration of these devices with standard CMOS, and we need more of this, more MPW runs provided so that we can advance the circuit design. Transfer learning is the early demonstrator, a lot of challenging problem to look at. Spike-based algorithms have reached excellent performance in software. So all the stuff I described, but translating them to IC is a promising research avenue. And we also need to look at the IO, the on-chip communication, asynchronous communication, and some work and open source type of activities needed so that everybody can build their own chips, because it's a little bit complex part. So with this, I'll conclude my talk and we are open to questions.
Thank you, Vishal. We have 3 questions which have been posted till now on the chat. One is, can you please touch upon the challenges of using STDP learning in multi-layer SNN and any potential solutions?
So as I described, let me show you here. STDP comes with winner take all, and it does very well as long as you are limited to 1 or 2 layers. It doesn't scale to higher number of layers because there's no global feedback, right? So there's no way. It's like there's no way to funnel back the error so that these weights can correct themselves. But so it's more like clustering, where it learns various weights by some sort of clustering implemented in spike domain. It is robust to catastrophic forgetting, but it will not give you deep learning like accuracy. And one goal of neuromorphic IC is that we should be able to compare with deep learning IC and benchmark. If we cannot reach those accuracies, especially for large data sets, then they will not be attractive. So these are the challenges. Now, as I said, STDP can be morphed into a 3-factor learning rule. I didn't have time to go through that, but you can go through some of the papers I have referenced. But STDP can be modified through a 3-factor learning rule, which can use global feedback. But everything has to be casted in the framework of backprop. Backprop is your guiding algorithm overall. So STDP has to be fitted with backprop if you want good performance.
The question which has popped up now is, how long do you think, how long does it take to program the whole matrix of weights on a typical implemented system till now? I know it's a very hard question to answer.
So, these arrays are barely, the papers just came out last year. We are working on our own chip design. So we haven't designed full array where we are doing ISPP. We are working on our tapers. As I said, very recently only we are able to fabricate these kind of circuits. Prior, we were just working with, 1-hour arrays, and they were not, you want them to be reliable to be able to build circuits. So still very early. How long will I can refer to the papers? I'll refer you to this paper. That's the only paper actually which talks about this here, and not very much details. And again, a lot of these things fall into proprietary, IP. So you will not see many of these things revealed. You probably have to design on your own. But this is the paper to look at.
This is somebody asking for a repetition. Could you explain again why SNN solves the solution for nonlinearity matrix multiplication in crossbar?
That's okay. So let's see. It's similar to PWM, PWM motor control. If you're trying to control something which is nonlinear and you apply analog inputs, it will distort the analog signal you are applying, right? But if it is PWM, you only have 2 levels. And if you put 2 points on a nonlinear response and draw a line, is always a linear line. So Spike solves that. Let me go to that slide. Here, right? So for example, here, this is the analog transfer curve. But if I'm working with 2 levels, let's say 0 and 2 volts, I just have this point and this point. And all I need to draw is a straight line, which is linear. So going to PWM or, any such pulse coding gives you linearity, but you're trading it for something else. You're trading it for complexity and time.
Thank you.
It's a common technique used in image sensors also.
Yes.
Right? Yeah. It's a standard technique.
There's a question from Sahiba Kaur who asks, what do you actually gain by using multi-valued conductance states in bi-mode for temporally encoded SNN circuits?
Okay, what do you gain? So, as I said, at every point, we need to ask the question, why are we doing this? Right? What is the advantage of doing this over, let's say, binary implementation using SRAM or flash memory, or binary actually you can do with DRAM type cells also. So you really, to make a compelling case for RRAMs, you really need multi-level with high density to be able to favorably compare it to other type of memory such as NOR flash. And if you don't have multi-level cells, at some point your classification accuracy of the model will drop if you binarize the network. So also binary weights have been done. The problem is solved. You need to look at multi-level cells. So many answers to that. But to get better performance, you want multi-level cells. That's the trend.
I'll take one more question. There are a number of questions are just propping up as we talk, but this will be the multi-million-dollar question. And if you can answer or if you can guide them, which is the most promising technology for RRAM? This is from Roberto.
So everyone is working on OxRAM. Yeah, OxRAM is the one because CBRAM has worse retention problem. And recently there's a lot of excitement about FEFET. We are yet to look into FEFET. Again, we can't do anything with it till it's integrated into Foundry CMOS. So OxRAM is the one which is available actually. So you can only work with what is there.
Good. There are other questions on the board, but I would request you guys to contact Professor Saxena directly, and I'm sure he would be happy enough to answer the questions, particularly on variability as well as backpropagation techniques. Thank you, Vishal, for a very interesting.
For some of this, I will refer the audience to the survey paper. These slides will be posted, right?
Wait.
We will post these slides, right? So you can go through the survey paper. There's somewhere.
Well, one of your survey paper I use as my teaching lecture note. After
so
teaching
this survey paper, there's another one in TCAS, and hopefully, if I get my act together, we might have a book coming in a year. But till then, you can look at the survey paper.
Good, Vishal. Many thanks for this interesting lecture, and have a good day.
Yeah, thanks. Thanks for having me.